This is Janae Crawford speaking on behalf of Team 52 and CS 4641 at Georgia Tech regarding our attempt to use machine learning to classify brain tumors. For some background information, the problem statement is fairly straightforward. The American Society of Clinical Oncology estimated that roughly 25,000 individuals will be diagnosed with either brain or spinal cord tumors in 2021 alone. So this amount of prevalence of these tumors, combined with the current diagnosis process, which requires doctors to manually review images from MRIs or CT scans, really emphasizes a need for accurate automation. The most pressing thing that this would address is with the faster diagnosis and patients' ability to begin treatment sooner, this could be completely game-changing, especially for the more aggressive types of tumors. So to talk about our data set, we basically combined two different data sets from Kaggle to hit at least 10,000 images. They were divided into the same exact categories with meningioma, pituitary, and glioma tumors, and then also a no tumor section. One thing I want to really reiterate here is a glioblastoma, a subtype of glioma. This is one of the most aggressive brain tumors to the point where the 2-year survival rate for glioblastomas is less than 2%. This means that of all people diagnosed with glioblastomas, if you look at them 2 years from diagnosis date, more than 98% of those people would already be dead. So this is just a really good example of how catching it early and beginning treatment early could be a really big deal for this type of tumor. Just as an example of what's in our data set, these images were intentionally selected to show both the 3 types of tumors and the 3 different imaging planes present in our data set. Then with no tumors, roughly half of the no tumor section appears healthy. One thing I just want to point out with the one in the middle is that while in the same imaging plane as the one on the left, they're both axial, this one does have pretty obvious eyeballs. So this presence of the eye socket versus no eye socket makes a big difference in our model that we'll see a little bit later. The one on the right is actually not from our data set, just because while I know that after speaking with neuroradiologists that we do have several brains with MS in our data set, this one is one I pulled online just to make sure that we're getting an accurate representation of this. This is a brain that doesn't have a tumor but does have multiple sclerosis. So it's an example of the no tumor yet unhealthy brains that are in our data set. Then with CT scans, they're characterized by this thick white ring around the skull, as you see around the brain, which is the skull, as you can see in this image to the right. Our data set said that it was MRIs, but again, after speaking with Drs. Jason Allen and Brent Weinberg at Emory, we learned that a lot of these images in our data set are actually CT scans, like the one right here. The big thing to note here is that they show less contrast than MRIs, which in general isn't a big deal. But with the lower grade, smaller, earlier stage tumor, it could be a lot more difficult to actually diagnose it. But since our data set classifies by type of tumor, not grade of tumor, and there's not really a good way for us to pull the CT scans out of the data set, we elected to just keep them in, but note that it could be a source of error. This brings us to the method section. So basically, we started with combining the data sets and then using PCA and dimensionality reduction to get ready for k-means. The goal here was to use k=4 for our 4 categories, to cluster images by tumor type, and then analyze with the elbow method to determine the optimal K. The results from this prompted us to totally rethink how we were doing things. So then moving forward, we decided to sort by imaging plane and then resize and normalize to get ready for NN and CNN. With k-means, again, we did k=4 on our first attempt, and then did the elbow method to determine a more optimal value of K, and the silhouette scores to confirm that value. And the 2 values that we thought were the best from this were k=2 and k=5, so we basically just ran k-means again with those 2 values instead. And then we totally rethought our data set moving forward for NN and CNN. The main thing to note here is that we did elect to manually divide our data set into 3 different subcategories based on the imaging plane, and then resize the images initially to 224 by 224, but then to 112 by 112, so basically in half the size again after running into some issues with CNN. But after the data pre-processing, it was basically just creating the model and modifying the layers. And again, basically the same thing as NN, just subtle differences for what those layers actually are. For reference, there's screenshots of some of the different planes for architecture for the NN and CNN. So now for the results. With k=4, this should have been conceptually the 4 different categories from our data set, but instead we see the 3 different imaging planes, sagittal, coronal, and axial, but then axial is further subdivided basically into axial plus eye sockets or axial without eye sockets. Then with using the elbow method, it looked like either k=5 or k=6 would be best, and we confirmed the silhouette scores that k=5 was better than k=6, but also k equals 2 was supposedly really good, so we ran with both of those. With k equals 2, this could have conceptually been tumor versus no tumor, but as you can see, that's not really what's happening here. It's still looking at imaging plane. It looks like sagittal on the top row and axial on the bottom row, so it's not really clear where coronal would be classified in this particular group of clusters. With k equals 5, we're back to using all three imaging planes as separate clusters. We have sagittal and coronal, which aren't really subdivided, and then axial is subdivided still into no eyes versus eyes, but then further into some of the no eyes section also appear to be brains with multiple sclerosis. Again, we can't confidently diagnose this without being professionals, but the last 2 to 3 especially do have a lot of those similarities from the multiple sclerosis brain shown earlier. And then for NN, we actually had quite high accuracy. The lowest accuracy was in the coronal plane with 84%, and we were expecting to see roughly 60 to 70%. And for reference, here's a classification report and confusion matrix for each of the 3 planes. Then with CNN, we did even better with NN. The lowest accuracy here was in the sagittal plane with 89.3%. And for reference, the classification report and confusion matrix for the 3 different planes. To reiterate, the major sources of error that we've talked about throughout basically come from the fact that our dataset is so heterogeneous. We have both CT scans and MRI slices which show different things and are designed to do different things, so the inclusion of both at the same time is a little bit risky. The CT scans again have both reduced contrast and varying skull visibility to add variety to the data. And then within the MRI slices, you have both imaging plane and the slice location within the imaging plane. For example, the axial where eye sockets are visible versus axial where eye sockets are not visible. And then with the no tumor section, we have roughly half healthy brains that don't have anything at all and half unhealthy brains where, while there's not a tumor, there is something going on there. And also with the extremely high accuracy that we see in NN and CNN in our models, this is probably a lot to do with how we ended up with smaller data sets. Because again, we started with roughly 10,000 images and then divided that into 3 different subcategories. So with these smaller data sets, it provides more opportunity for overfitting, which artificially inflates the accuracy. And another potential source of error could be the way that we divided by imaging plane. Since we did that manually, we could have made some mistakes. In sum, while k-means wasn't a great model in terms of classifying the tumors, it did show us a lot about our data set and what the computer naturally sees, even if we don't see those same things. So this prompted us to reach out to the neuroradiologists, where we learned a lot more about the data set and some of the problems that we were having, which prompted us to, moving forward, divide the data set into the 3 different subgroups and then run NN and CNN. And then CNN performed a little bit better than NN, but since we had an inflated accuracy on both of those, we definitely need to rerun this with larger data sets to confirm. Some other ideas for future work. First, with CT scans, since that kind of threw off the data a little bit in our current study, it would be beneficial to maybe use these same models, but looking at just MRIs or just CT scans. With k-means, it seemed to cluster quite well, just not what we were wanting to cluster. So it would be interesting to try to cluster after dividing the data sets by imaging plane. And then with 3 and 4, these are things that could be helpful for accuracy, but may harm our ability to use this model in real life. For example, with the no tumor section, if we remove the unhealthy brains, this would probably improve accuracy because there wouldn't be as much to throw off the model. But, I mean, most people, when they get MRIs, they don't get them for no reason. So in reality, it could make it a lot harder if the model is just really not capable of distinguishing between something that isn't a tumor but is unhealthy. To conclude, I'll just leave the references on the screen, and thank you for your time.